All right, I think we can get started now. I'd like to thank everyone once again for joining us on this week's Smart Webinar series. Our speaker today is Dr. Jared Shooter from NETL. Jared is a senior data scientist at NETL with a background in statistics. Has spent more than a decade working on interesting problems related to machine learning and AI approaches. Jared is also one of our co-leads for the SMART effort, and he's going to be talking. He's going to be giving a really interesting talk today. This is related to a talk that he gave back in the fall to an SBE workshop on applying AI and machine learning to oil and gas problems. And so he's going to be talking today about evaluating variable importance in black box models, and comparing strategies there. So without further ado, Jared.
Well, thanks, Grant, for the introduction, and thanks, everybody, for taking time out of your day to listen to this talk. What I'm going to be presenting today is basically some work that we've done at NETL on a Department of Energy project with Texas A&M. And I'm going to be talking about variable importance, basically. So how do you identify which predictors in your model are the most important for predicting a particular response of interest? And in particular, I'll also be talking about some ways we came up with for dealing with time-dependent responses, like how do you measure importance over time. So my collaborators on this project, Luan Lin is a research data scientist at NETL. She's the one who did the bulk of the work that I'm going to be presenting. Srikanta is the domain expert and principal investigator on the project. And of course, you know him from being on the advisory board of the SMART initiative as well. I just provided my opinion a lot about things, whether it was desired or not. And then I'm documenting, of course, things that were done, like in this presentation. So, okay, we'll start off with just some basic motivation to this problem. As you know, our predictive modeling tools are becoming a lot more robust with machine learning, deep learning, and variants thereof. Also, because of that, we're able to model more complex phenomena, and also, of course, we're gathering a lot more data nowadays. And so we're increasingly in these situations where we have a lot more predictors than we used to have, and we may not have a lot more observations necessarily. So this ratio of P to N is kind of growing. And as you know, the more predictors you have relative to the amount of data that you have, you're going to get more unstable estimates of any kinds of parameters of interest. You're going to potentially have issues with interpretation or inference when you have less power or evidence available. And then also, if you want to do any kind of thing like optimizing a response where you would do some kind of a search through the variable space to find some optimal response, you now have way more dimensions to search through. And also, you know, due to Occam's razor, you expect, and I've seen this in practice, that typically most responses are going to be primarily driven by a small number of inputs. You know, we might have other ones in the model. They contribute some information, but primarily it's just a few that are really important in most cases. Okay, so, you know, a typical way people will deal with this is by doing feature selection, or dimension reduction. You want to take all the predictors that you have and reduce them down to a smaller number. You know, a lot of the popular approaches that are out there tend to have some disconnect with what the current reality is. You know, first of all, we're using black box models a lot more, and many of these methods are tied to specific types of models. And so if you're using that type of model, it's great. But if you're using some other model, the approach doesn't apply anymore. Also, of course, some of these transformation methods where you take essentially weighted linear combinations of all of your predictors. Those really don't make it much easier to interpret what's going on, especially when the interpretations you want are for the the natural predictors coming into your model. So sometimes those approaches may not be applicable for you. And then also, of course, I alluded to this at the beginning. If you have some kind of time or even space-dependent response, how do you even think about the importance of a predictor when it might change depending on time and space? Many or most strategies that I can think of are kind of assuming a constant or static importance of a feature. So just some background on this project. As I mentioned, it's a larger project where we're collaborating with Texas A&M. This particular study was just a part of that project, and we're basically trying to figure out, first go through the literature and identify what are some more model-free or model-agnostic methods for measuring the importance of your variables, and then how do you handle importance over time that might be changing. And also, we wanted to just kind of test them out on a particular problem from the oil and gas domain. And so I'll show some results later on a CO2 injection simulation, just a really basic simulation to kind of verify that these approaches are giving the results that we expect. Okay, so to illustrate these methods, I just made up a problem so that we know what the truth is, or at least we have a sense of what the truth is. What I did was just simulate three variables over the span 0 to 1, so we don't have to worry about centering and scaling our data or any of that. And then what I did was I mixed, for each of them, I applied some function to them and then added them together to get the response y. And so the shapes of the functions are in these plots on the left. You can see the first one is kind of an absolute value distance from 0.5. The second one is like a logarithmic kind of shaped increase, or exponential shaped increase, I mean. And then the third one, I just simulated some white noise and then one. So that variable should have no impact on the response, would be the conclusion. And then the weights that I mixed them with, so I applied a weight of 5 to the first one, so we might expect that one to be most important. I put 3 on the second one, which would be almost like roughly half of the importance, and then the last one I just mixed it in with a weight of 1. And so from this function, I sampled 100 different observations, which are shown in the bottom right. Those are like the marginal views of the response as a function of the each of the different predictors. The points that are in red are the training data, which was 80%, so 80 of the observations. And then the blue points are 20% test set, which I used to evaluate, at least for one of these methods, I used it. So what I'll do now is just kind of step through, there were 6 different methods that we used to evaluate variable importance. I'll just step through each of them, describe them at a high level. Of course, these slides will be available after the talk if you want to dig into the equations a little bit more, if I leave something out. Or if there are questions at the end, we could certainly go back. But I'll describe the method and then show the results on this data set, and we'll see if they kind of give the expected result. Okay, so the first 2 methods I'll talk about are basically, it's the same idea. The concept is if a variable is important in the model, then including it in the model should improve the goodness of fit of your black box model, which seems kind of obvious. So the goodness of fit measure that we used in this case was a pseudo R-squared. It's basically just the, how well your model fits, or how well it models the variance compared to the natural variance in the data, the error variance. And so what you do basically is you break the relationship that the variable has with the response in one of 2 ways, and then you just look at how much the model suffers. The thinking being that if this variable is really important and you break its relationship with the response, it's going to be a really bad model then, and you're going to see a large reduction. If the variable didn't really matter, then it doesn't really matter if you mess with the values. So the 2 variants that we used, one of them is remove. So this would be where you just you have one model fit with all of your variables, and then you have a second model that's fit leaving one of the variables out, and you're just going to see which model is better, or how much better the full model is than the removed model, sort of like what you would do in stepwise regression. The other one is a permute strategy, where you take the values of that variable across the predictors and you just scramble them up randomly. And again, whatever relationship that predictor has with the response is now going to be completely broken by doing that. And that's sort of similar to what would happen in a random forest if you're doing variable importance for that. It does something similar with the out-of-bag samples in each tree. Okay, so the results that I got from using this on that simple example earlier are shown below. We took 80% of the data to train the models, and then evaluated the R-squared on the 20% held out test set. And I did that for the full model and for the model that either had the variable removed or had the values permuted. And you can see that for the most important variable, which we know is x1, you see a very large reduction in R-squared going from the full to the altered model, which is what we would expect. Going from the full to the altered model for x2 also shows a reduction, but not quite as much. And then for x3, you can tell that when you remove it, actually the model gets slightly better. And I did forget to mention, so I'm using a gradient boosting model in these examples as the black box model. And so anyway, over on the right, you see the two R-squared loss values. Larger means it's more important. And so here, at least for these methods, we get kind of the expected result. Okay, so those R-squared loss methods are more measuring variable importance at a global level. We're looking overall at whether this variable is important in the predictive quality of the model. These next couple of methods I'll talk about try to look more at the importance as it changes across the support of the variable that you're looking at. So the idea here is, if you if you range over the support of a variable of interest and you integrate out the effect of all the other variables that are in the data set, then what you should get is like this marginal relationship between the predictor and the response. And if that relationship looks interesting in the sense that it's not really flat, if it is really increasing a lot or really wiggly, then that means this predictor is important. And so, this equation here, basically you're fixing the value of your variable of interest across your data set, and then you're just averaging over the empirical distribution of all the other predictors in the model, which is, when you just average over the values that they have in the data set, that'll be like integrating over the empirical distribution. Okay, so what we have here are the results using this partial dependent plot method over the data set. What you can see is that the results that come out, the shapes of these relationships look fairly similar, I guess, to what the true shapes are that we know of. You get this kind of V shape for the first predictor. The magnitudes of these values are larger than the others, which tells you that it's more important. The standard deviation, which is what I'm using to measure the variability or the interestingness of this function, is larger for that predictor. And then for x2, it's got a similar kind of pattern to that exponential rise that we saw before, but it's not quite as large, so the standard deviation is a little smaller. And then for the third predictor, we get what we would hope for, which is essentially a flat relationship. This predictor doesn't have anything to do with the response. So in this case, not only do you get kind of a global importance measure, which is the standard deviation I calculated here, but you also get a sense of what the shape is of this relationship with the response, and maybe an indication of, where within the support of each of these variables, where it's kind of most important. Okay, but the issue here is, when you fix the value of one of these variables, you're basically integrating over all the support of all of your variables, and it's possible that maybe if the the predicted response curve is kind of interesting in different parts of the space in different ways. You may not want to do this kind of global level integration. And so this fourth method I'll talk about is called accumulated local effects. And the idea here is that you want to kind of just integrate over a small window of that input space around the variable, the value of the variable of interest that you're looking at. So now instead of this sum here going over all the observations in your data set, now you're just going to go over the subset of observations in your data set where whatever variable you're looking at has a value that's pretty close to the one that you're sticking into the prediction, the one that you're fixing at. So you're kind of basically doing a partial dependence plot, but within a small region of your data set rather than over the whole data set. And as you can expect, what you're going to get out of that is a prediction that it might be, on the one hand, it's going to be less biased because you're looking at more local behavior. On the other hand, you have less data that you're averaging together. So you're going to have more unreliable or variable kinds of estimates of the importance. In this particular case, it seemed like we had enough data because the shape of these functions looks pretty much identical to what it did for the partial dependence plots. And again, measuring the standard deviation of these functions, you end up with values that are very similar to what we got for the partial dependence plots. So, what's good about these two methods that I just showed is that they run pretty quickly, and so you can get these estimates fast. And as I mentioned before, you can also see the shape of the relationship, which is, helpful. It's interesting. All right. These last two methods that I'll discuss are a bit more complicated, and also I think the way we use them is not really the way they were originally intended. So both of the next two methods, this first one's called LIME for Local Interpretable Model Agnostic Explanations. Both of these methods, the goal is really to look at a specific observation and understand why it got the prediction that it did. And so we're more looking at local behavior in the black box function, just right around one of the observations in the data set. And so this model, or this approach, LIME, basically the idea really is, if you imagine you have this function, f of x, where you pass in your inputs x, and you're going to get this prediction f of x. This is really just kind of doing a numerical estimation of the gradient of that function along each of the dimensions, which are the variables in your model. And then if you look at the size of that gradient in each direction, you can figure out which variable is locally the most important. And that's really the idea. The assumption here, I guess, is that you're going to do this perturbation or you're going to look around an observation in a window where you would expect the prediction surface to be more or less linear. And so then you can fit an interpretable model just in this small window and get the importance of the variables around that observation. So the way that it works is you start with one of the observations in your data set, you perturb it by just sampling around it within an appropriate window, sampling across all of the variables in the model, and then you just fit like a linear function. A ridge regression model is, I think, the default for this package I used. You just fit a linear function, and then you look at the coefficients in the model to see which ones are the most important and which ones are the least important. And the way we then calculate the importance of the variables across the whole data set is just by averaging the absolute values of those weights in those local models. So the results here, the plot on the left, this heat map, this is what was produced by the R package that I was using. So what's actually happened here is each of the variables in the model, x1 through x3, were discretized into 10 different intervals of equal length. And so the sampling, this perturbation around an observation, happened within that bin on each of the three axes, the three different variables. And then that's what was used to fit the local model. And so this top third of the heat map are the 10 different bins for X1. The middle third is for X2, and the bottom third is for X3. And then each of these cases, which are the columns, these are the training observations in the data set. They're only going to have a weight for one of those bins for each of the predictors, whatever bin they fell in. And so that's why it kind of looks this way. And they're all scrambled up because the observations have values and they're not sorted or anything like that. So to try to visualize this a little bit better, what I did was I took for each case, I pulled off its value for X1, X2, and X3, and I plotted the weight of that variable on a scatter plot, and that's what you see in this middle column of plots. And again, you basically just see the same relationship that we have seen on the PDP plots and on the ALE plots. You see this V shape for the first one, this kind of sinusoid for the second one that's approximating the exponential pattern, and then more or less flat line for the third. The kind of step function appearance of these is just that's happening because I discretized these variables into the 10 different bits. And again, the average absolute values of the weights across the observations actually, kind of comes out to be more or less the same sort of thing that we saw in the other methods. All right, so the final method I'll talk about is called Shapley additive explanations or Shapley values. The idea here came from, I guess it came from game theory, but the concept in my mind is really similar to what it is for Lyme. Basically, if you're looking at a particular observation, you want to describe how, the prediction at that observation is going to be different than what the prediction is at the global average, like the globally average prediction across the data set. And so for this observation, you want to kind of take that difference between the predicted value for that observation and that global average and kind of divvy that up among the different variables in the model, which is basically like just fitting a local linear model or something in my mind. And so just as a basic example, like if your black box model was just a linear model and you took the form of the function here, which is this first sub-bullet, and then you took the mean prediction, which is the same equation, but just with the expected value of the three random variables plugged in there, and then you took the difference of the two, the importance or the contribution of each of these predictors is just going to be the difference between the observation and its mean times the coefficient in the model. And so, that makes sense. Like the coefficient in the model and how far it is from the average, that's basically kind of explaining how important this variable is. And so if you kind of repeat this for a general black box model, then of course you can't just do some kind of analytical solution like that. You're basically, again, using this idea of integrating over the empirical distributions of all the other inputs in your model, and then trying to look at this difference between the prediction and the average overall. So, here the basic idea is you're going to kind of loop through all possible subsets of your inputs, or the variables in your model that don't include the one that you're interested in. And then for each of those subsets, you're going to compare what's the prediction when I include my variable of interest with that subset, and what's the prediction when I don't, or basically when I integrate over my variable of interest to kind of remove its effect from the model. So this thing within the sum is almost like like what we're doing for R-squared loss when we, like the permute method maybe, where you're just, or the remove method, I guess, where you're kind of integrating out the variable of interest and comparing the model quality before and after. But then this outer, like the sum is just kind of looping through all these possible subsets and integrating over the empirical joint distribution of the variables that are left out of the subset. It's very slow to run because it's a lot of like combinatorial sorts of things involved in the loop to get all these subsets and loop over variables that they have within the data set. It also doesn't scale well, it seems like to me, but the results, as you see, they come out, they look pretty good. Again, same sort of shapes, same sort of importance score at the end. If you look at the average importance values, or the absolute values of them, I guess. I have a typo there. Okay, so looking at a summary of all 6 of these methods, what we found is basically, for this data set, all of them are performing roughly the same. You have like similar ratios of importance scores between different pairs of the variables in the models. You can see that I think it might be by chance that the Lime and the Shapley value approaches produced values so similar to the PDP and the ALE approaches, but you can see at least that the 3 different pairs of approaches kind of give different magnitudes of values, but the ranking and the ratio between the values is roughly the same. So that's good to see. This at least verifies that the approaches seem to be capturing what we think they should be. And so the question that we tried to address on this project that I'll talk about is, what do you do if the response is varying over time or analogously over space, but we didn't really address that. You know, the issue you're going to run into is that a variable's importance is often treated as a static property of that variable, but over time, there's no guarantee that that relationship is with the response is going to be the same at all time points. And so you could approach it as just you could average across all time points and just say that's the importance of the variable. But is there a way to get more nuance and kind of figure out how its importance is changing over time that might allow better insight into what's going on? And so to test this out, we pulled out a data set that we had from a past project a number of years ago. Priya Raviganesh, who's on task 3 of SMART, actually simulated this data back then. This was a CMG simulation of a CO2 injection into just a basic closed reservoir. There were 9 inputs that were varied over the simulation, which are primarily just talking about the relative thicknesses, permeability, and porosity of the reservoir and the cap rock, plus the anisotropy ratio, like to describe flow in the horizontal and vertical directions, and then the injection rate itself, and also this indicator to help describe how the layers in the reservoir were stacked up. In this case, the response that we're going to look at over time is the average pressure in the reservoir. The simulation itself runs for 30 years, and it has 19 time points, kind of logarithmically spaced, as shown here in the, the grid cells are logarithmically spaced as well, but the time points are primarily all at the beginning and then spaced out more toward the later years. The data sets that I'm going to show here, we had generated 2 space-filling designs. So a maximum and hypercube sample and a maximum entropy design. The reason they're 97 runs is because at the time we were comparing them to a Box-Benken experimental design, which also had 97 runs. So we just combined these 2 data sets to create one data set with 194 runs. And then we also had an independent run of a Latin hypercube sample with 97 runs. So that's what we used as the test data set. And in this case, also the black box model that we're using is a Kriging model. So it's assuming a trend term, which we used a quadratic polynomial for that. And then it has this correlation term Z. And for that, we are using this standard Matern correlation for that people use a lot in Kriging modeling. Okay. So, one thing you can do, and we tried this and it works, is you can throw in the time step as just a 10th predictor in the model. You can fit that model, But of course, if you look at any of these variable importance approaches on your data set, you're going to find out, hey, time is the most important variable in the model. And everything else is going to have very low importance. And you could look at those importance scores, which are all really close to 0, and try to compare them, but it doesn't seem like a good idea. Like they might be kind of unstable estimates. So we wanted to say, hey, is there another way to explore variable importance in this kind of situation? And so what we ended up trying to do was to fit a separate black box model at each time point, and then use these approaches above that I described to measure the importance of each variable at each time point. And then we use the strategy to allow us to compare importance across time points for those different variables. I do think there are other ways that this could be approached as well, though. So this is what we tried. And so the way we framed this problem is, first you're going to get, at each time point, you're just going to get this raw importance score, which is the output of the 6 methods that I was describing before. You got your R-squared loss, where the raw score is just the difference in the full and the altered, or the original and the altered model. You've got the 2 partial dependence and accumulated local effects plots, where what I showed was this continuous case in the example I had before, which is just the sample standard deviation across the plot. If you have categorical data, you can use this rule. You look at the range over 4. That's like a reasonable estimate of the variability of that plot. And then for the Lime and Shapley value approaches, as I showed before, we just took the average of the absolute values of the weights. So those are the raw scores that you get, which are the ones I showed before. So what we do first is, like, if you think about the R-squared loss model as an example, one concern that we had was, if your full model is really a crummy model and it only has an R-squared of like 0.2, then the R-squared loss that you measure is going to be not so informative. Whereas if your full model fit very well and had like an R-squared of 0.95 or something, then R-squared loss maybe carries more weight. And so for those methods, at least, you can think about normalizing that raw score by taking the, dividing by the R-squared of the full model. So measuring it as not the loss directly, but as like a % loss. And that would help to normalize across different values of R-squared. Similarly, for the other 4 methods, if you were trying to think about like what's going to cause this variability in the PDP plots or the ALE plots to get larger or smaller, remember they're kind of plots of each of the variables against the response. So maybe dividing by the average value of the response at that time point will help to kind of get them all on a similar scale across time points. And then the same kind of reasoning holds for the Lime and Shapley value approaches. So for those 4, we just divide by the average response at that time point to try to get them all closer to looking the same to begin with here. And so those are all what we're calling normalized importance scores. And then what you can do is, if you want to compare the importance across time or across the predictors, then you can divide by another normalizing constant that is different depending on what your goal is. So if your goal is just to compare across the predictors at that specific time point, then what you can do is just divide by the largest normalized score in that time point. And that's what we're calling the relative importance score. So this is going to scale everything from, assuming your normalized scores are positive valued, this would like scale everything to the interval 0, 1, where the best predictor importance is going to be 1 always at each time point. Alternatively, if you wanted to compare the importance of predictors across time points, then rather than dividing by the largest importance at that time point, you're going to divide by the largest importance across all the time points and all the predictors. So this kind of puts all the predictors' importance scores on the same scale to compare across time and across the predictors simultaneously. So what's good about these scores is, of course, this is just a monotone transformation of the importance scores. So any ranking or prioritization of the variables is going to be the same. If you take ratios of the importance scores under each of these formulas, you're going to get the same ratio. It's really just rescaling the response or the importance scores to help you compare them. So, here I'll just step through the results from each of these 6 approaches for this data set, the simulator that we were looking at. Remember, we're looking at the average pressure as the response of interest. And so what we see here with R squared loss, the remove variant, the uncertainty importance factor, which is the kind of global comparison metric, is shown here in the blue. And then the relative importance score is in gray. And so you can see that the relative importance score at every time point, one of these variables has a value of 1 for that score. So within a time point, they're like nicely spread out. You can compare them. Whereas for the uncertainty importance factor, there's only one place that it hits 1, and that's the injection rate around time 13. But the shapes of them are pretty similar. What we see here is that at the beginning of this process, as we're injecting CO2, the primary driver is the reservoir thickness, which makes sense. This is going to control how much pressure is building up. Eventually, as the plume kind of hits the cap rock thickness starts to matter. And then as the process continues into the later time points, it's really the injection rate that starts to drive the pressure buildup. At that point, because the plume's kind of saturated everything, and now you're just packing a bunch of CO2 into a space and building up the pressure. Here are the R squared loss values when you permute. Again, very similar results. The shapes look pretty much the same. If we move to the partial dependence plot, and so here you see the shapes are largely the same, but they kind of come out looking a little bit different. These are a lot smoother, it seems like, than the R squared loss, but the conclusions are largely the same. Here's the ALE plots. Again, this is almost identical to the PDP. The Lime results, very similar, and the Shapley value results, very similar as well. So these last 4 really gave very similar results, which isn't so surprising because they're looking at very similar things. Okay, so in summary, what did we do? We compared these 6 different variable importance methods. We found that they give fairly comparable results, which is a good thing to see. We developed these 2 measures to allow you to compare importance across time and across predictors. The relative importance score, which kind of normalizes by time point, and the uncertainty importance factor, which normalizes globally. We use those to evaluate the impact of inputs on this CO2 injection reservoir simulation. And we found what I said before, basically the early part of the process, it's the thickness of the reservoir and the cap rock that drive the process, but later on, it's primarily the injection rate. In terms of what we learned using these methods, so the R squared loss, to calculate that, it's going to require you to fit 2 black box models, the full model and then the one where you altered the variables. So, and that's actually for each variable, I should say, you have to fit 2 models. I mean, the full model you fit once, but for each of the variables, you have to fit an additional model. So it can be a bit slower depending on the training process for your black box model, but it does, it's pretty straightforward to interpret the results, and it allows you to get like a global view of the importance. The PDP and ALE approaches were very similar. They're both very quick and kind of straightforward. They also show the relationship between the input and the response, which is nice. The Lime approach was a little bit slower, not so bad, but it's kind of driven by how much permutation you want to do and how finely you're dividing up your windows for across the variables. With Shapley values, I found it to be a lot slower, probably because of all this combinatorial searching. Both of them gave pretty similar results, but again, I think they were made to explain the predictions on a single observation, not so much to measure importance across the entire support of your variables. But you can use them that way, but it seems like that's not the intended use. So if I was going to suggest what to use, I found ALE to be pretty nice, as long as you have enough data to do that averaging over these empirical distributions within these windows. If you don't have as much data, then maybe these partial dependence plots are a better way to go. But then R-squared loss also is a good, based on looking at the importance scores being at slightly different scales for those methods and the shapes of the importance over time being slightly different for those, I feel like they might give a good orthogonal view or semi-orthogonal view of the importance across the data set. So I would suggest those as well. And of course, these RIS and UIF methods, we found them to be interesting, and they're pretty straightforward to interpret. So the final slide here I have, how can all this apply to SMART? Well, of course, we're going to be developing a lot of black box models. We're going to have a lot of predictors potentially. We want to be able to understand what's the most important predictor so that we can maybe limit our focus to understanding and characterizing that relationship between that predictor and the response. That's going to allow us to do this rapid prediction that we need on so many of the tasks. And also, of course, we're dealing with data that's going to vary over time and space. So we're going to have to be able to handle that in some way. And with that, that's what I got. I could take any questions. Thank you.
Yes. So I had a quick question about the toy problem, sort of the toy problem that you had at the beginning. And and I noticed, that for X1 and X2, all the shapes that you created based on most of the approaches that you use, they are sort of flat at the lower values and the higher values. Then they are closer to 0 and closer to 1. Is there some sort of like an end effect that when you're doing these predictions that something like that happens? I was just curious if you had any sort of insights why the results look flat, when your X1 and X2 are closer to 0 and to.
Yeah, I had noticed that too. I didn't dig into it a lot, to be honest, but I mean, in looking at the samples that were taken here, I mean, at least on the right-hand side of X1, which is where I noticed, hopefully you can see my mouse here, where I noticed a lot of the flatness, it does seem like the higher sampled values are in this test set, and the first two R-squared loss approaches I used, I was measuring R-squared on the test set, but for the other methods, you actually just need the trained model, and then you're just making predictions off of that model. So for the other four methods, I was only using these red points to fit the model. So my guess is that this the model fit is going to be kind of flat toward the end of X1 at least, because those blue points weren't included in the data set. If that makes sense. I'm not sure why the X2 kind of has this sigmoid shape, but maybe it's a combination of, again, the sampled points and then also the interference with the other two variables, the X1 specifically, that might be causing it to look different there to the model.
Okay, thanks.
Sure.
Hey, Jared, this is Raj. Quick question. So it looks good in terms of, there is always this challenge of how do you capture the time dependence or importance as a function where the things are changing with time. In your example that you showed, have you looked at pressure, in addition to pressure, other things, for example, like saturation, and whether that changes because the underlying physics changes a little bit, and also if not, what are your thoughts in terms of whether any of these methods would have any challenges there?
Yeah, so the simulation, we kind of had three different summary level responses of the entire reservoir. There was the average pressure, which we looked at. There was also the maximum plume radius, which we did look at that a little bit. And then also the total storage efficiency, which I think would probably most directly apply to the saturation that you're talking about, although the plume radius, I guess, tells you where it is. But what we did find for the plume radius response that the importance of the variables was not quite so interesting. It was primarily the same variables kind of dominating for the majority of the simulation. So the results I'm showing here, I thought they're just a little bit more interesting because you can actually understand why the importance changes. We have not looked at the total storage efficiency as far as I know, not over time like this at least. But yeah, in terms of whether you'd run into any issues with the methods, I mean, clearly everything I showed here is for like a univariate response. It would certainly be a lot harder to try to extend them to some of the volumetric responses that we're getting on our task at least. But that would be an interesting thing to look at.
Yep. All right, thanks.
Sure.
Hey, Jared, this is Shrikanta. I just wanted to add to your response.
Yeah, go ahead.
Yeah, so Raj, basically, chiming back to what Jared said, that we had these three responses, and we have actually looked at the temporal evolution of these three responses. And so the average pressure basically, builds up once the system goes from infinite acting kind of a behavior to a bounded system, which is the way we modeled it. So obviously the dependence switches from like a diffusive type dependence to a storage capacity oriented dependence. So which is why the importance changes. And then the maximum plume radius kind of settled down quite quickly in terms of how far the plume goes. And the dependence is not as much of a time dependent. The importance is not very time dependent, as is the case with the total storage efficiency. And these are the kinds of things that we would see very, very well in the Yakima TSPA, where the early time dependence would be sort of waste package dependent, and the importance would be waste package dependent, and the late time would be the far field related dependent. And so this is just one way of elucidating that dependence. And on the plots that Jared showed, you can see how the importance of a particular variable changes as you go through time. And this is where you can actually link it back to the physics and basically ascertain that these importances and these dependencies actually make physical sense.
Exactly. Yeah. Yeah, so that's the thing. Right? I mean, you basically want to make sure that you're capturing, and you're right. I mean, in terms of the physics, some of it would evolve at different time scales and have different effects. But the variables that drive those and the important variables that come out of these analyses, do they make sense physically? And so it's good to see, these kind of things. Actually, yeah, it does make sense.
Yeah. In fact, as you think about what we're doing in Task 5 to look at physics-informed machine learning, and so this is yet another way in which you fit a time-dependent proxy and then say that can I capture these kinds of things as constraints in my model, and do these make sense as far as the underlying physics are concerned?
Yeah, and I'll say also, like if you were trying to you'll run simulators at certain, input combinations, and or if you're collecting field data for that matter on some of the other tasks, and you're trying to fit these models, it may be important to kind of make sure you have good coverage of certain variables at certain parts of the process that you're trying to predict. And so, in this case, you might prioritize getting runs that are going to cover these reservoir and cap rock thickness variables if you wanted to understand that early process of pressure buildup. But if you were looking longer term, maybe you make sure you have good sampling across the injection rates to drive down the error of the models.
Hey, Jerry, may I ask a quick question about the simulation you run over there? You use 194 samples for simulation runs. So I just curiously how you did that. So you kind of running all the simulations and you based on results to start the analysis, or you run some simulations of 194, even just half of that, and you start building a model and then to do analysis, or how you do that curiously?
Yeah, so we had these runs laying around we had these runs laying around from a previous study. So they had already been run. We didn't do any kind of sequential running or anything like that.
Okay. Yeah, because I think kind of one point is, if model is actually time saving not really much, not much taken for the simulation itself, so that's okay. But if model is actually a full scale, maybe we kind of think a little bit of how much we spend on that. If we can start dynamically or sequentially to do the build and then to do analysis for the import, maybe something we can maybe interesting over there, I guess. Anyway.
No, you're right. I mean, you could do like a small simulation, number of runs here, fit these importance curves, and then maybe that will tell you where to kind of do additional runs to drive down your error. Sort of like you might do with Gaussian process modeling, sampling in parts of the space where you have the most variability in your predictions.
Yeah, that's right. Yep.
Okay, great. Does anyone have any last questions for Jared? We're coming about to the end of our webinar time. Okay.
Hi, I have one last question. Sorry, just this year from ERC. I go to your slide that in one slide you hold one variable at the mean value, and you use all the combination of the other variables to evaluate the contribution of that variable.
Yeah, this Shapley value approach here.
Next slide. Next.
Oh, up here.
Yeah. So how do you do this?
Yeah. So I mean, here this definition here really kind of explains that these this val function that's evaluated over a set of variables. What you're basically doing here is you're taking all the variables that are not in your set and you're integrating over them. That's this integral of f hat here. And then you're comparing that to the average prediction. So remember, this approach, you're kind of comparing the prediction at an observation to the average prediction globally and trying to explain what that difference is across your different variables. And so, in this case, that's kind of what you're doing. You're looking at a subset of variables, you're integrating out the ones that aren't in that subset, and then comparing to this average and trying to parcel it out among the variables that are in the subset. So that's what that blue part that I have there, that's kind of what's going on there, is like for that subset, you're including your variable in the first case, and you're integrating over your variable of interest in the second case and comparing that difference. That's going to tell you how important the variable is. And then this green part is where you're kind of summing over. This is like a combinatorial thing. You're basically looking at all the values that you have in your data set for all your different variables, and you're taking all the combinations of them that appear in order to do this integration. So that integral is really just, that's what this sum is. You're just kind of summing over this, basically the joint distribution of all your variables, the empirical joint. And then this red part, this is where now the subsets that you're looking at are pulled from, it's some subset of the predictors that aren't the variable you're interested in. And so that's where this can get time consuming, because you might just choose like one other variable, or you might choose a couple or a few, and then you have to look at all of those. And so that's why it just takes forever. Like even in this case, it took a few seconds, even though I only had three variables in the model and not a lot of data.
Yeah, thanks.
Hope that helps. Yep.
Yeah.
Cool. Well, thanks everybody for your time. I appreciate it.
Yeah, thank you. Thank you, Jared, and thanks everyone else. A great talk and some interesting questions and discussions. So hope everyone has a good rest of your afternoon. Continue to wash your hands and practice social distancing, and we'll talk again next week, if not sooner. Take care.
Great. Thanks.
Bye.